We are discussing about GATE 2002 ECE paper, and this question is related to electronics. Look at the circuit diagram. Each transistor in the figure has a DC current gain of 50, that is beta DC is 50, cut-in voltage V gamma of 0.65 volts and VBE saturation of 0.75 volts. The output voltage V0 for T2 in saturation can be as high as 0.2 volts. Assume 0.7 volts drop across a conducting PN junction. Determine A. Minimum value IB2 necessary to keep T2 in saturation. B. The maximum permissible value for the resistance RB1. The worst case high input and worst case low input for which T2 will be either in saturation or in cutoff. These three things we are going to calculate. So first of all we will see about the A bit, the minimum value of IB2 necessary to keep T2 in saturation. Whenever the T2 in saturation, the maximum voltage is given as the output voltage V0 for T2 in saturation can be as high as 0.2 volts. It was given. So this is 0.2 volts. At this point you are getting it as 0.2. And by that time if it is 0.2, you can calculate the current flowing through this IC2. Current flowing through IC2 is nothing but IC saturation, because the transistor is in saturation. By that time this is plus 5 volts. Okay, so it is it is not given, it is plus 5 volts. So 5 minus 0.2, 5 minus 0.2, that is VCC minus VCE saturation divided by 1 kilo ohm, which is nothing but IC saturation is equal to 4.8 milliamperes, and IB is equal to IB2 minimum. IB2 minimum is nothing but IC saturation divided by beta. So IC saturation is 4.8 milliamperes divided by beta value is given as 50. So which is nothing but 96 microamperes. So the minimum base current required to keep the transistor in saturation is 96 microamperes. Next one. The maximum possible value for which for the resistance RB1. Now we will go for the second one. The maximum permissible value for the resistance RB1. So look at this given diagram. We are going to calculate RB1 value. So this value we are going to calculate. Okay, so what we are going to say for this resistance is nothing but normally the resistance across this one is such that, okay, and the voltage across this one, okay, should not be greater than something as VB1, such that VB1 voltage is going to be such that at the time T2 must be in off condition. Okay, so to make the maximum permissible value for the resistance RB1, so assume that one, when the transistor T2 in saturation, when T2 is in saturation, whenever it is in saturation, at that time, by that time you will get it as VBE saturation, and since it is in saturation, at that time diode will be in forward bias because the base current is providing. Diode will be forward bias, and here you will get collector base junction of T1 transistor will be forward bias. Okay, so there will be just on of a collector base junction, and so that current coming from this VCC plus 5 volts, this VCC plus 5 volts, the current coming from this one is going into the base of, that is collector to base junction, and through this diode and through this T2, like this it will flow, such that VB1, how much voltage it requires, VB1 is equal to collector base junction cut-in voltage just comes into the on condition, collector base junction, such that no current will flow through towards emitter base junction, VCB cut-in plus V diode voltage forward bias plus VBE saturation. This is V cut in is given as 0.65 and diode voltage is 0.7 and VBE saturation is 0.75. So it will be equal to 2.1 volts. So if the voltage across that point is going to be 2.1 volts at that time, okay, the T2 transistor comes into on condition. To make the T2 transistor comes into on condition, at that time the voltage across VB1 has to be 2.1 volts. Okay, so the value of RB1 should be such that the current flowing through it has to limit. So for example, the current flowing through it is going to be I. Okay, so we are going in this way. I minimum, this is going to be the minimum current such that the voltage across this one is not going to be equal to such that, just wait, okay, and it is not I minimum, and make it as I itself. Okay, this is make it as I itself. So the meaning of calculating RB1 maximum permissible value of resistance, such that if we know the current flowing through R at that time, that voltage difference should be, okay, lesser than 5 minus 2.1. So that if you are going to say, let us assume VB1, what we have calculated, VB1 is 2.1 volts. So here you must get minimum of 2.1 volts. Okay, if you are choosing RB1 very large, at that time what happens, voltage drop across this one is going to be large, such that the voltage drop across VB1 may be reduced below 2.1, such that, so that whenever it is going to be happening in that way, T2 will not be in saturation. So to make the T2 in saturation, the minimum voltage you must maintain at VB1 has to be 2.1 volts, such that you can use a maximum value of resistance, so that voltage difference this one is going to be at most 5 minus 2.1, that is nothing but 2.9 volts must be the voltage drop across RB1, not more than that one. If it is lesser than that one, it is much better, but the worst condition, RB1 should be maximum such that the voltage drop across that one should be 5 minus 2.1, at most 2.9 only. So how to choose that one? For that one we should know the value of I. I is the current which is flowing through this diode, and the same current, this is the current because the current is flowing through collector base junction and through this diode, so that is the I current, which is nothing but IB2. Okay, it is dividing now into two currents, one is IB2, the other is nothing but, this is, let us assume, I1. So we can write I is equal to IB2 minimum, okay, plus I1. So IB2 minimum already we have calculated, that is nothing but 96 microamperes plus I1. I1 is the current flowing through this 15 kilo ohm resistor. So we can calculate VB saturation is the voltage drop across base of T2. So this point is nothing but VB saturation. VB saturation is 0.75 volts. So we can write VB saturation minus of minus 2 divided by 15 kilo ohms. So this will be around 96 microamperes plus 0.7, 2.7 divided by 15. So it will be around it will be around 2.8, 0.19. It is 0.19 milliamperes, 0.19 milliamperes, and if you add these things, it will be around 0.2 milliamperes. So the current flowing through the resistor is 0.2 milliamperes. Now the voltage drop across that resistor, I into RB1, should be, the voltage drop across this one should be lesser than or at most equal to VCC minus VB1, which is nothing but 5 minus 2.1, and it has to be I is nothing but 0.2 milliamperes. So this is 0.2 milliamperes multiplied by RB1 should be less than or equal to 5 minus 2.1, that is 2.9. From this one you will get RB1 should be less than or equal to 14.5 kilo ohms. 14.5 kilo ohms. So RB1 maximum is equal to 14.5 kilo ohms. If you choose the maximum value of RB as 14.5 kilo ohms, at that time what you are going to be getting is VB1 as 2.1. If you are choosing lesser than that one, VB1 will be greater than 2.1 volts. That is sufficient enough. So maximum permissible value of RB1 is 14.5 kilo ohms. Now third bit, worst case high input and worst case low input, such that T2 will be either in saturation or in cutoff. That we are going to check now. Okay, so first of all assume that one. So worst case high input. What is meant by worst case high input? Worst case high input, that is nothing but this is a high input. Generally logic values are going to be indicated in this way. This is low level and it is high level. So worst case high input is nothing but this is VIH minimum. Okay, this must be such that the output will be at low level. So what must be the minimum value of high level you are applying, such that T2 will be in, that is output will be in low level, that is nothing but T2 will be in on condition, that is saturation. So worst case input high is nothing but that makes T2 will be in saturation, so that output will be treated as logic low level. Okay, so for that one, T2 in saturation is nothing but how much voltage it requires at VB1, just now we calculated. Okay, to make T2 into on condition, voltage drop across VB1, that is nothing but over this point VB1 is equal to 2.1 volts. That is voltage drop across VB1 to make T2 in saturation is VCB cut in plus VD forward bias plus VBE saturation. That is what we have seen as 2.1 volts. Okay, and that is nothing but base of T1 is at 2.1 volts. That implies nothing but now you must apply this VIH minimum such that, okay, you are going to be, now I will draw the only T1 transistor over here so that it will be better understood in this way. This is T1 transistor whose base is going to be at 2.1 volts, and this is base and it is emitter side. Okay, and this is collector. So this junction is JE and this junction is nothing but JC. So generally what we are expecting is nothing but to make T2 into T2 in on condition, at that time current must flow in this direction only. By that time JE must be reverse bias. So how much voltage across this one you can apply, that is what must be VI maximum, such that you can apply emitter base junction has reverse bias, such that the current is flowing through collector base junction, that makes the transistor T2 in on condition. Okay, so V input, this is NPN transistor. So NPN is nothing but this is N and base is of P type, and emitter base junction reverse bias is nothing but, okay, emitter is at N side, emitter must be more positive, so V input must be greater than 2.1 volts. That is emitter voltage should be greater than base voltage. Okay, emitter voltage should be greater than base voltage, such that emitter base junction will be in reverse bias. Whenever V input is at 2.1 volts, that is nothing but VE emitter voltage is greater than 2.1 volts and base voltage is at, okay, 2.1 volt. That is nothing but N side you are applying more positive voltage and P side you are applying less positive voltage. That makes emitter base junction reverse bias, so that transistor T2 in will be in saturation region. will be in saturation region. Okay, so VE has to be greater than 2.1. At most you can go for VE. Worst case VE is nothing but VE minimum, that is nothing but VIH minimum. Worst case high input is nothing but 2.1 volts. 2.1 volts. If you give 2.1 volts, at that time JE may become forward bias. By that time the current will go through forward bias emitter base junction. No current is flows through collector base junction, such that diode will be reverse bias, T2 will be in off condition. So to make T2 into on condition, you must maintain V input as minimum as 2.1 volts. So VIH minimum as 2.1. If you give more than that one, we can ensure that T2 will be in saturation. This is the worst case high input, VIH minimum. Similarly, we can calculate VIH maximum. Okay, VIH maximum. Now we will see. Now look at the same diagram. Worst case low input. Now we are going for worst case low input. Low input is nothing but, here you are applying the low level. Low level is nothing but, again we are going with same thing, voltage levels can be indicated. This is high voltage level and it is low voltage level. Now we are interested in the low voltage level. Worst case low voltage level is nothing but VIL maximum. What is going to be the maximum input voltage you can apply across emitter of T1 transistor, such that this V0 will be at high level. V0 will be at high level because you are applying low level. Low input is nothing but it is inverter, so output will be at high level. Output will be at high level is nothing but T2 must be in off condition. Okay, and we have seen that one, the voltage required at the base for the T2 on condition is nothing but 2.1 volts. So again we are going for the same situation with T1 transistor, and this is base 1, whose base 1 voltage is nothing but 2.1 volts. So that transistor T2 comes into on condition and emitter voltage you are going in this way. So T2 must be in the off condition. So T2 must be in the off condition is nothing but T2 must be in off condition. The meaning of that one is nothing but emitter base junction of T1 must be forward bias and collector base junction of T1 must be reverse bias. So no current is flowing. This has to be reverse bias. Okay, and this must be forward bias. So the current is going now in this direction. So no current flows in this direction. Current is 0. So that current is 0. Base current is 0. Transistor will be in off condition. So what is the maximum voltage you can apply across emitter? Across emitter, such that emitter base junction is forward bias. Okay, so emitter base junction has to be forward bias. To make the emitter base junction forward bias, this is emitter. Okay, so you can think it as NPN transistor, so that it is N type and this is P type. So this is the general diode symbol with E and with B, that is nothing but N side and P side. So where it requires some voltage like this, cut-in voltage, which can be called as, okay, so VE is equal to V gamma plus VB. We can write VE is equal to V gamma plus VB. So V input has to be less than or equal to VE is equal to, P side voltage should be such that normally we know that one, voltage across P side is nothing but voltage across N side plus cut-in voltage. Here voltage across P side is nothing but voltage across base, voltage across N side is nothing but voltage across emitter side, and V gamma of 0.65 volts. So now VE is going to be minimum. VE maximum is equal to maximum is equal to VB minus 0.65. So that is nothing but VB is 2.1 minus 0.65. So from this one we can write it as VE maximum. VE maximum is 2.1 minus 0.6. So it will be around how much is given? Cut in voltage. Cut in voltage is 0.65. So 2.1 minus 0.65, which is going to be written as 1.35 volts. So this is worst case. Low input is nothing but you can apply 1.35 volts across n side, such that we can ensure that emitter base junction is always forward bias. If you apply more than that one, at that time the emitter base junction comes into forward bias. Now there will be no current flows through the emitter base junction, comes into reverse bias, no current flows, so that T2 will come into the on condition. So the worst case low input required to make the output high, that is nothing but to make T2 off, is nothing but 1.35 volts. So this is the right answer for this one.